Good day and welcome back for part 4 of our discussion on maximum and minimum values. And we're finally to the point where we've set the stage for finding the absolute maximum and minimum values of a continuous function on a closed interval, which we are guaranteed to exist by the extreme value theorem. And we have a very nice procedure for doing so. The first thing we need to do is find the critical points of the function f. And let me remind you what a critical point is for a function f. So in order to be a critical point, C needs to be in the domain of f with one of two things occurring. With either f prime of C equals 0, and that's the more typical case, or f prime of C is undefined, which is a more subtle type of critical points. Once you find the critical points, we find the value of f at each critical point between A and B, because that's one type of location where we might expect to find that absolute max and min. The other possible location would be the endpoints. So we determine the function value at A, the function value at B. And combined together, steps 2 and 3 give you a list of values. And from those list of values, i.e. numbers, you pick the largest, that will be the absolute maximum. You pick the smallest, that will be the absolute minimum. Let's illustrate this idea with a nice concrete example. Let's find the absolute maximum and minimum values of this given polynomial on the closed interval from 0 to 2. And note this is a continuous function on a closed interval, so it's exactly what the above procedure is made for. In fact, this function is something that we've already worked with in the previous example. So without recreating the work, let me just note from the previous page or the previous video, there is a single critical point. The only critical point is x equals 1. And note, x equals 1 is in between 0 and 2. So we must determine the function value at 1. So substituting 1 into our function, we would have 1/3 1 cubed minus 1 squared plus 1. 1/3 minus 1 plus 1 is simply 1/3. We also need to, according to step 3 of the above procedure, evaluate f at 0 and evaluate f at 2. So substituting those into our function, we would have f of 0 is 0, and f of 2 is going to be 1/3 2 cubed, so think 8/3, minus 2 squared, so minus 4, plus 2. So in this case, we would have 8/3 minus 2, which is positive 2/3. And looking at these values, 1/3, 0, and 2/3, we need to pick the smallest and the largest. The smallest would be f of 0 equals 0, which we would indicate as being our absolute minimum. And the largest would be at 2, which we indicate as being our absolute maximum. And this is exactly what you would have to indicate for me. Once you have that list of values, just circle whatever the smallest one is and right next to it absolute minimum. Circle whatever is the largest and right next to it absolute maximum. So with that in mind, let's go ahead and look at another example. We have a continuous function, t times the square root of 4 minus t squared, on this closed interval from minus 1 to 2. What I would like you to do is to pause the video, give yourself 3 to 5 minutes, and see if you can follow our 4-step procedure to find the absolute maximum and minimums of this continuous function on the closed interval from minus 1 to 2. And hopefully at this point you've paused the video and you've done a bit of work. And let's go ahead and walk ourselves through the details. So f of t is a function t times the square root of 4 minus t squared. And remember, when it comes to determining critical points, they are values that are in the domain of the function. So in terms of our function f, all we would really have to worry about is whatever we are taking the square root of cannot be negative. So t squared has to be less than or equal to 4. And what that tells us is the domain would be from -2 to 2. If t is larger than 2 or less than -2, then this inequality will not be satisfied. So the critical points are going to be found by looking at the derivative. And in order to differentiate this function, we are going to take our time with it, and it's going to require a combination of differentiation formulas. And this is the scenario I alluded to earlier this semester, where differentiation is now just a part of the problem, not the entire problem that we're asked to solve. It just plays a supporting role. So using the product rule, we think the derivative of the first times the second plus the first times the derivative of the second. Now I'm going to go ahead and just write out that derivative to make sure that we don't make any silly mistakes. So we would have the square root of 4 minus t squared, and when we differentiate the square root of 4 minus t squared, we need to use a chain rule. Inside function 4 minus t squared, outside function square root. So we take the derivative of the outside function, 1 over 2 square roots, we evaluate it at the inside function, and we multiply it by the derivative of the inside function. So note the 2's cancel, and in that second term we can combine those t's together in the numerator and go ahead and write this as minus t squared over the square root of 4 minus t squared. And if we are purely interested in just finding the derivative, of course we have it. But what we're going to want to do is take this derivative and set it equal to 0 and solve for t. So I want to get it into a more simplified form. And the simplification that jumps out to me is I have two terms. One of them is a fraction. Let's go ahead and combine this into a single term. So our common denominator would be the square root of 4 minus t squared. So we'll multiply that first term by 1 so that we get the desired common denominator. And note it works out extremely well because the top will be the square root of 4 minus t squared times the square root of 4 minus t squared. And when you multiply those together, you're simply left with 4 minus t squared. And then we're subtracting away another minus t squared. So the formula for our derivative would be 4 minus 2t squared, all divided by the square root of 4 minus t squared. And in order to find the critical points, what we would like to know is where is this derivative equal to 0, and where is this derivative undefined. So we'll first think about where it's equal to 0. Remember, a fraction is only equal to 0 when the top is 0. So 4 is 2t squared, 2 is t squared, so t is equal to plus or minus the square root of 2. We also need to think about that more subtle type of critical point, which would occur when f prime is undefined, but you're still in the domain of the function. And let's just note that this is undefined when the denominator is 0. So the other type of critical point we could get is when 4 minus t squared is 0. So that would give us t equals plus or minus 2. And note, the function itself is defined at plus or minus 2. The derivative is not. So we really do have, in this case, 4 separate critical points that we need to be concerned with. So in terms of where we evaluate the function, we are only interested in what happens in this interval from -1 to 2. So in terms of the critical points of interest, and let me summarize, we have -2, minus the square root of 2, positive square root 2, and 2. -2 and minus the square root of 2. these critical points are not in the interval from -1 to 2. So when it comes to evaluating the function, we do not need to worry about those critical points. They are not of interest to this problem. What we do need to evaluate is the function at the endpoints of the interval and any critical points in between. So 2, in a sense, is playing kind of a double role here. It's a critical point, and it's also the endpoint of the interval. And if we're to go ahead and evaluate the function, so just substituting these values in, we'd have -1 square root 4 minus 1, which is minus the square root of 3. If we substitute in square root of 2 for t, we have square root 2 times the square root of 4 minus 2, and square root 2 times square root 2 is 2. And f of 2 is 2 times the square root of 4 minus 2 squared. 4 minus 4 is really 0. So we have our list of function values. From that list, we pick the largest and the smallest value. So they're right next to each other, so I'm just going to go ahead and circle them simultaneously, and right next to them, absolute minimum, absolute maximum. And I would suggest that this is a fantastic example to make sure you understand. It illustrates this procedure we have for finding those absolute maximum and minimum values of a continuous function on a closed interval. And it's a scenario where the differentiation is a bit involved. It requires some good rules of differentiation. It has both types of critical points that can occur, and even some that we have to throw out because they are not in our interval of interest. So there really is kind of a lot going on in this problem, which means it's a perfect opportunity for you all to do some practice. So besides the suggested problems, which I know you are working through, there is also a class worksheet that you can find on Canvas related to maximum and minimum values. So I suggest taking a look at that worksheet, give yourself a solid 25-30 minutes to work through it. The next video we'll go through a few of the examples, but you can also find typeset solutions on Canvas covering the remaining ones. So stay tuned and take care.